It's wild to think that a simple patch of warm ocean water can transform into, well, a storm that can reshape entire cities. Today, we're going to break down one of the most powerful phenomena on Earth, the tropical cyclone. So, how does that happen, right? How does the ocean, which can seem so calm, give birth to something so destructive, so organized? Well, the answer is to think of a tropical cyclone as this colossal heat engine. It's literally sucking up heat energy from the sea and converting it into the raw power of wind. And, just like any engine, it can't start on its own. It needs a very specific set of ingredients. So, what's the recipe? Turns out, scientists have figured out there are count 'em, six crucial conditions that have to line up just right for this engine to roar to life. Okay, ingredient number one, and this is the big one, the fuel. We are talking about a deep layer of really, really warm ocean water. It has to be at least 26.5 degrees Celsius, that's 80 degrees Fahrenheit. And listen, this isn't just a thin little layer on the surface. We're talking deep warmth, because that's what provides the sustained raw energy a cyclone needs to get going and keep growing. So you've got the warm water, right? That makes the air above it super unstable and moist, just ready to shoot upwards. But a column of rising air isn't a storm. It needs to spin. And that's where the Coriolis effect comes in. That's just the spin of the Earth itself giving it a little nudge, a little twist. Now, to protect this baby storm while it's trying to form, you need calm winds way up high, what meteorologists call low wind shear, so it doesn't get ripped apart. And last but not least, you need a little something to get it all started, like a pre-existing weather disturbance, a seed, if you will. You get all six of those things together, that's when the heat engine can really fire up. All right, so the engine is running, the storm is getting stronger. How do we measure just how powerful it is? Well, the tool we all know is the Saffir-Simpson scale. It's that 1 to 5 rating you always hear about, and it's based purely on one thing, the hurricane's maximum sustained wind speed. When you hear forecasters talk about a major hurricane, they're talking about anything category 3 or higher. And that's when you get winds strong enough to cause just devastating damage to buildings. And this is so important to understand, that category number only tells you about the wind. That's it. It tells you absolutely nothing about the storm's other deadly threats, things like its size, the storm surge, or how much rain it's going to dump. And so often, it's the water, not the wind, that's the real killer. And this is exactly why a storm's category just doesn't tell you the whole story. I mean, not even close. To really get what I'm talking about, let's look at 3 historic storms where the category number was honestly just the start of it. Let's start with Hurricane Katrina. Now, it made landfall as a powerful category 3. But the real catastrophe, the thing we all remember, wasn't the wind. It was that massive storm surge that just overwhelmed the levee system in New Orleans. The flooding that followed was, it was biblical. It became the costliest hurricane in U.S. history, causing a staggering $100 billion in damage. Okay, then you have Hurricane Harvey. It slammed into Texas as a Cat 4, a real beast. But its biggest threat wasn't the wind at landfall. It was what happened next. It just parked itself over land for almost 5 days, unleashing this relentless, absolutely historic amount of rain. Harvey didn't just break the U.S. record for rainfall from a cyclone, it completely shattered it. We're talking over 60 inches of rain. Think about that. That's 5 feet of rain in some spots. It caused this catastrophic freshwater flooding even hundreds of miles away from the coast. And then, get this, just a few weeks after Harvey, Hurricane Maria barrels into Puerto Rico as a monster Category 4. The winds were, of course, devastating. But the real lasting legacy of that storm was the total, complete collapse of the island's entire power grid. It plunged millions of people into darkness, not for days, but for months. The initial death toll was reported as 64, but the reality was that the long-term lack of power, of clean water, of basic medical care, it led to a revised official estimate of nearly 3,000 deaths. It just goes to show, each storm's legacy is totally unique, and the consequences ripple out long after the storm has passed. So that's the past. What about the future? Well, scientists are now taking these lessons and using them to model future risks. They're creating these scenarios that basically combine the worst parts of past storms into something plausible and, frankly, terrifying. Let's take a look at one of these. They call it Hurricane Melissa. This scenario imagines a storm that's just on another level.
It's fueled by unusually warm oceans, and it's so powerful that it just completely overwhelms our modern defenses. All our infrastructure becomes basically helpless against its fury.
And this is where it gets really scary, because it illustrates that combined threat we've been talking about. Imagine the winds of a top-tier Category 5. Now add a Katrina-level storm surge. And on top of that, add the slow-moving, nonstop rainfall of a Hurricane Harvey. You wrap all of that into one single catastrophic event. And that brings us to a final and I think really critical question. Look, our science is getting incredible. We're getting better and better at forecasting a storm's path, its intensity. We can see it coming. But are we as a society getting any better at withstanding it? Because as our world keeps changing, the answer to that question, well, it's going to define our future.